Imagine this. One day, everything you know, every star, planet, and galaxy, could either fade into an endless freezing void or come crashing back together in a cataclysmic collapse that undoes it all. Sounds like science fiction, right? But for nearly 30 years, most scientists bet on the cold, lonely end, the big freeze, all because of this mysterious force called dark energy pushing the universe apart faster and faster. Hey everyone. Today, we're diving deep into a cosmic plot twist that's shaking up everything we thought we knew about the universe's ultimate destiny. New data from one of the most ambitious sky mapping projects ever is hinting that dark energy, that invisible engine driving expansion, might be losing its power. Could our standard model of cosmology be incomplete? Is a big crunch coming instead? Stick around because by the end you'll see why this isn't just abstract physics, it could redefine our place in the cosmos. Let's explore how scientists might have gotten dark energy all wrong, or at least not entirely right. Let's rewind to the late 1990s. Edwin Hubble had already shown us in the 1920s that the universe is expanding. Galaxies racing away from each other like dots on an inflating balloon. But the big question was, would gravity eventually pull it all back, slowing things down? Many expected a deceleration. Astronomers turned to standard candles, specifically Type 1, a supernovae. These are thermonuclear explosions of white dwarfs in binary systems that always detonate with roughly the same brightness. By measuring how dim they appear versus their known true luminosity, and factoring in redshift, how their light stretches as space expands, teams could calculate distances and recession speeds across cosmic time. In 1998, two independent groups, led by Saul Perlmutter, Brian Schmidt, and Adam Riess, analyzed over 50 of these explosions. And the distant ones were fainter than expected, meaning they were farther away. Shockingly, this proved the expansion was accelerating, not slowing. Some unknown repulsive force was at work, dubbed dark energy. This earned them the 2011 Nobel Prize in physics. To make it relatable, think of throwing a ball upward on Earth. Gravity slows it until it falls back. But here, it's like the ball keeps speeding up into the sky forever. What could cause that? Einstein's cosmological constant, lambda, a property of empty space itself, got revived as the leading suspect. It fits into the lambda cold dark matter, lambda CDM model, our standard cosmology framework. Quick breakdown. Visible matter, stars, planets, us, is just approximately 5%. Dark matter, invisible stuff we detect only via gravity, is approximately 27%. Dark energy, a whopping approximately 68%. Dark matter clumps things together, dark energy rips them apart. Cold just means the dark matter particles move slowly. Picture this real-world parallel from everyday life. I once talked to a friend who's a long-distance truck driver. He described how, on a flat highway, you set the cruise control expecting steady speed, but subtle hills or wind resistance make it vary. Dark energy was like that constant throttle, assumed unchanging. But DESI data suggests the engine is sputtering. Growing up, I was fascinated by backyard stargazing in my small town. One clear night, I pointed a cheap telescope at Andromeda and felt tiny. Years later, learning cosmology made me realize that tiny doesn't even cover it. The universe's scale is humbling, and our models are like maps that seemed perfect until new roads appeared. A more scientific example comes from the cosmic microwave background, CMB, the afterglow of the Big Bang. Discovered accidentally in 1965 by Penzias and Wilson while tweaking a radio antenna. They thought pigeon droppings were the issue at first. Combined with supernova data and galaxy surveys, it painted the lambda CDM picture. Fast forward to recent breakthroughs. The Dark Energy Spectroscopic Instrument, DESI, mounted on a 4-meter telescope in Arizona, is a marvel. It can capture spectra from 5,000 galaxies at once, building the largest 3D map of the universe ever, nearly 15 million galaxies from its first 3 years of data released in 2025. DESI tracks baryon acoustic oscillations, BAOs, fossilized sound waves from the early universe, like ripples frozen in the cosmic web. These act as a standard ruler. By seeing how this ruler stretches over 11 billion years, scientists measure expansion history precisely. Combining DESI with CMB supernovae and weak lensing, gravity-bent light from distant objects, the results are intriguing. As dark energy's influence appears to have weakened by about 10% over the last 4.5 billion years. It's still pushing, but less aggressively, like easing off the accelerator while still moving forward. Why does this matter? If dark energy is dynamic, not constant, lambda CDM needs tweaking. Maybe it's a quintessence field that evolves, or modifications to general relativity on huge scales. This ties into ongoing Hubble tension, different methods giving slightly different expansion rates today. Let me share another relatable anecdote. Think of climate science. Early models assumed certain constants for CO2 effects, but feedback loops, melting permafrost releasing more methane, changed predictions. Similarly, evolving dark energy could flip cosmic forecasts. One researcher I recall reading about compared it to realizing your GPS uses outdated maps. You might end up on a different road entirely. To add depth, particle physics might intersect here. Could new fields or forces from beyond the standard model explain it? Experiments like those at CERN or future colliders could link micro and macro scales. Or, as some suggest, it might highlight limits in our understanding of vacuum energy, quantum fluctuations predicted to be huge but observed tiny, the cosmological constant problem, one of physics' biggest headaches. Imagine the human impact. If we confirm a changing dark energy, it reframes existential questions. Civilizations pondering the stars for millennia assumed permanence. Now, our models evolve with better tools, reminding us science is iterative. A colleague once told me about simulating universes on supercomputers. Small parameter tweaks lead to wildly different fates, from eternal expansion to recollapse. Visualize the 3D DESI map. Earth at center, dots as galaxies, each with hundreds of billions of stars, blue for distant, white for nearer. Flying through it feels like navigating an infinite city of light. BAOs show as density patterns, seeds for the cosmic web we see today. Filaments, clusters, voids. If weakening continues and dark energy goes negative, expansion halts, then reverses into a big crunch. Everything compressing back, heating up, potentially to a new Big Bang in some cyclic models. Contrast that with the Big Freeze. Galaxies isolate, stars die, black holes evaporate via Hawking radiation, leaving a dark, near absolute zero expanse after trillions of years. Or the Big Rip, if it strengthens, atoms torn apart. These aren't certain, but they spark wonder. Personal insight. This uncertainty motivates me. In a chaotic world, cosmic mysteries remind us humility and curiosity drive progress. Right now, confidence is building but not definitive. DESI alone is around 2 sigma, approximately 95%. Combined data hits 3 to 4 sigma. Physics demands 5 sigma for discovery, like the Higgs boson. Remember the 2011 faster-than-light neutrino hype? It was a cable glitch. Caution is key. Euclid satellite, Nancy Grace Roman Space Telescope, Vera Rubin. Observatory's supernova hunt. In 5 to 10 years, we might have clarity. This doesn't break cosmology, it refines it. Science thrives on anomalies. It could unify gravity with quantum mechanics or reveal new physics. Optimistically, it suggests the universe is more dynamic, perhaps with cycles of rebirth rather than heat death. The universe's story isn't written in stone. Our understanding evolves with better data and open minds. Embrace uncertainty. It fuels discovery. Whether big freeze or crunch, it underscores cherishing our brief, beautiful existence and continuing to ask why and what if. What do you think? Peaceful fade out or dramatic crunch? Drop your theories below.